Welcome to the 14th meeting of Cryptography Club. This is our last meeting for this year. We will talk about the full code for the RSA encryption and decryption and cryptography communication on computers. Let's look at the full code first. Here is the full code for meeting 14. So there are 4 examples here for the big number n and the public key e. These examples all work, so we could try any one of them. But for the 4th one, it takes more than 4.5 minutes to calculate phi and 25 minutes to do the ED check. So we don't need to do the 4th one here. It's still possible though. Right now we have n is 39 and e is 5. These 2 are the smallest ones and they'll be the fastest. So here are the steps we need to take for RSA. First, we need to find prime numbers p and q by prime factorizing n. And then we calculate phi n, which is p minus 1 times q minus 1. And then we check the public key e to see if it satisfies these 2 conditions. First, e has to be a whole number between 1 and phi n. Secondly, e has to be coprime with phi n. Step number 5, we check the conditions for private key d. ed divided by phi n needs to have a remainder of 1 and d needs to be greater than 0. After we have sorted out public key e and private key d, we see if m, the plaintext, is less than n. If it is, then we can start encrypting and decrypting. For encrypting, we do m to the power of e divided by phi n and get the remainder c, which is the ciphertext. And for decrypting, it's c to the power of d divided by n and get a remainder m, which is the plaintext that we generate again. So that's the whole process for RSA. Next, we have prime factorization. First, we're going to find prime numbers. So prime factorization within 100k only takes 0.29 seconds. The biggest prime number within 100k is 99,991, with 9,679 prime numbers in total. Within 1 million takes 6.64 seconds. The biggest prime number is 999,998, and there's a total of 78,703 prime numbers. So that's just some information. And then here for the code, this is the part we're going to use to find prime factors, or prime numbers in general. We import time because we want to see how long it takes. And then we have a empty list, which is num, and we're going to put the prime numbers in here. I equals 2 and k equals 100,000. So whatever I and k is, it's going to be the range that we're going to look for prime numbers in. So right now the range is 2 to 100,000. So 1 million for k is the maximum. That means 7 zeros. If you don't want to wait, use k with 6 zeros. Like, oh, right now it has 5 zeros. We can put 1 more 0. But for now we're going to do prime factors between 2 and 100,000. And then we do start equals time dot time to get a timestamp, and then now equals time dot time 2 because we're going to need to do now minus start in the future. So while now minus start is less than 60, because if it's greater than 60 seconds we want it to stop because we don't want it to take too long. And I is less than k, so if I is less than k, then we continue, because if it gets to 100,000 we want it to stop. And then we find the square root of I, because if we want to see if a number is a prime number or not, we just need to compare it to see if there are any numbers between 1 and square root of that number, and see if any of those numbers are factors of I. And I explained this in meeting 12, I think. So if you don't understand, you can look at that video again. Basically, we just need to compare numbers between 1 and square root I with I to see if I is a prime number. So for j in range starting from 2 to loop plus 1, because we need to plus 1 so that the loop is included. And we start from 2 because 2 is the smallest possible prime number. So we do I divided by j. If the remainder equals 0, then we break. That means that j is a factor of I, and I is not a prime number. So we don't want to include I. We only want the prime numbers. And then we do I equals I plus 1 and go to the next number. So, for example, if the next number is a prime number, then we would do this else and append I into the list for prime numbers. After we have finished all of the numbers from 2 to 100,000, the loop stops and we do now equals time dot time again to find the current time. And then we print generated list of prime numbers and took now minus start amount of seconds. And we print the list of prime numbers. And I'll show you guys. So they generated the list of prime numbers and took only 0.319 seconds. And then the prime numbers are in here. So the list is very long, starting from 2. And all of these numbers are prime numbers. And then after we have the list, we copy the list twice and give it to list A and list B. And then we reverse the list to make the list have the biggest numbers at the front. So we want to know how many prime numbers there are in the list. So we just need to do length num to see how many elements are in the list, because each element is a prime number. And then we print the 10 biggest prime numbers we do a loop, and then starting from 0 to 9, we print the 0th element in num all the way to the 9th element. So that would be the first 10 numbers in the list. So the 10 biggest prime numbers would start from 99,991 all the way to 99,877. So we have found the prime numbers we need. Now we can prime factorize other numbers. If you don't want to make too long, make big N smaller than 10 digits in decimal format. So big N is the number we're prime factorizing. So if we don't want to wait too long, then we make big N less than 10 digits. Decimal format is the format we usually use, like in everyday life, so we don't really need to change anything. The fundamental theorem of arithmetic is the core of number theory, also called the unique factorization theorem. It says that every integer greater than 1 can be represented uniquely as a product of prime numbers up to the order of the factors. So that means that any integer greater than 1 can be prime factorized, but not every single integer we try here can be prime factorized, because we're prime factorizing it with only 2 prime factors. But if we say we can use like 3 prime factors to find the product, then any integer greater than 1 can be prime factorized. But right now we're just seeing when 2 prime factors get multiplied together. So not everything can be prime factorized right now. In our code, 9,679 prime numbers times 9,679 prime numbers only takes 15 seconds, so it is relatively efficient. If we do these two multiplied together, which is like, I think, the 1 million prime numbers, If we tried the 1 million one, it would take 892 seconds, which would be a lot longer. Currently, this code only completes 10 to the power of 7 times 10 to the power of 7, which is prime factorization up to 14 digits in decimal format. So we can prime factorize numbers up to 14 digits, but if we want it to be efficient, then we do up to 10 digits. In the future, we can try to use dichotomy to find the number faster, because right now we're multiplying every single prime number with every single prime number to see if they have a product of the big N. But in the future, we could use dichotomy. Like, if this number doesn't work, we can try not the immediate number after it, but like a number between the biggest and the smallest number, and then going for the middle every time. That would eliminate things faster. So here is the function for prime factorization. The parameter is big N, which is the number we're prime factorizing. When we start, we do start equals time dot time, and then we have a loop with a loop in it. So for M and range length A, that is the first copy of the prime number list. And then for N in range length B, which is the second copy of the prime numbers list, we would do the mth A times the nth B. So in the first loop, it would be 2 times 2, because 2 is the smallest prime number in the list. And then we see if big N equals 2 times 2. If it is, we would return 2, 2, and print 2 times 2. But if it isn't, then we don't do this, and then we look for the next number, so 2 times 3, and then 2 times 5, all the way to 2 times the biggest prime factor. That would finish this inside loop for B. And then after we finish that, we would go on to the next loop for A, which is the outside loop. So 3 times 2, 3 times 3, and so on, until we try all of the prime numbers with each other. If any of them has a product of big N, then we would return those two prime factors, and it would be a successful prime factorization. But if none of the numbers have a product of big N, then we do now equals time dot time, and then print the amount of time it took, seconds, and this number cannot be prime factorized, and return 0, 0, because it still needs to return something. And then we do prime factorization for N. N, right now we have 39, because in RSA, the first step is to prime factorize P and N to find P and Q. So we prime factorize N to find P and Q. After that's done, we say prime factorization is complete, P and Q have been generated, and print P and Q. After that, we're starting to look at the public key E. Okay, so prime factorization is complete, P and Q have been generated. So P and Q are 3 and 13, and that is right, because 3 times 13 equals 39, which is N, and they're both prime factors, so we have prime factorized it successfully. Next, we're going to look at coprime. So this is the part for public key E. We need to see if E is coprime with phi n. So this is the function for seeing whether two numbers are coprime, n and m. It doesn't matter which one is bigger, n or m. Inside the function, we have t equals 0. While m is greater than 0, we continue this loop. We do n divided by m, find the remainder, and give it to t. And then give m to n and give t to m. If t equals 0, that means that one number is a multiple of the other number, and then m would equal 0 and the loop would finish. T would equal 0 eventually. And then when t equals 0, m equals 0, the loop stops, and we see if n equals 1. If it is, that means the two numbers are coprime, and we return true. If not, then it's not coprime. That's the function for determining coprime. Next is the function for calculating phi. So phi, if you remember, is just, if we're trying to find phi n, then it's the same as finding all of the numbers from 1 to n that are coprime with n. So that is the point of this function. We want to give n to num and then start with count equals 0, and then we do from 1 to num plus 1 to include the num, and in the loop we see if num is coprime with I. So starting from 1, we see if 1 is coprime with num, and then 2, and then 3. If it is, then we do count plus 1. After this finishes, we have a count, which is how many numbers less than num between 1 and num are coprime with num, and then we return that number. That would be the value of phi n. And then we find the value of phi n here by running the function. We give that to phi value. Right now n equals 39, so we have found phi 39. To check, we use the formula because we know that because 39 is a prime number, we can do p minus 1 times q minus 1. So 3 minus 1 times 13 minus 1. That would equal phi n, phi 39. And then we see if these two are the same. If they are, then the value is correct and we print the value. If not, then it's not correct and we need to check the code again. So here it is correct. The phi value equals 24. So 2 times 12 equals 24. So phi 39 equals 24. So now the phi value is finished. We're going to check the conditions for public key E. These are the two conditions. So for the first one, E has to be an integer between 1 and phi n. So we just need to see if 1 is less than E and E is less than phi value. If it is, then we will print it satisfies. If not, we print it does not satisfy and exit the code. Here, it satisfies the first condition. The second condition is E has to be coprime with phi n. So we use our function for coprime with E and phi value. And if the function returns true, then that means we print the condition is satisfied. If the function is false, then we print E is not coprime and does not satisfy condition. Right now, it returned true, so it printed the E is coprime with phi n and the condition is satisfied. So after these two conditions are met, we know that the public key E is one that we can use. So when E equals 5, it is a public key E that satisfies all of the conditions. And then now we have finished the public key E part, and we're going to check the private key D. So, and we need to calculate it because when we're doing it, we don't know what the private key D is, and we need to find it. So D has these conditions. So for example, we already know E equals 17, phi n equals 3120. Then the indeterminate equation turns to solving 17x plus 3120y equals 0. So that's like another situation. When E equals this and phi n equals this, then we need to solve this equation to find D, which is the x in here. So right now, E equals 5 and phi n equals 39. So we would need to solve 5x plus 39y equals 1. And then, so because we talked about in the previous meeting how this works, we can turn these into an equation and solve for x and y. And they always have a solution for it. So the parameters of the extended Euclidean function are a and b. The return values old s, old t, old r are x, y, and remainder, which is the GCD respectively. So this is the function here. We put in a and b, and we would get old s, old t, and old r, which are x, y, and the GCD. So we could run this function to find d, basically. This function is very useful because it solves the Diophantine equation and finds the GCD at the same time. The GCD will always equal 1 because we know that a and b are coprime with each other, so their greatest common divisor would be 1. A and b corresponds to e and phi n, and then we just need to run this function to find x, y, and GCD. So we run it with e and phi value and get x, y, and r. So x, y, and r is one pair of solutions for the equation. So we print the solution with x, y, and r. So one of the solutions would be x equals 5, y equals -1, and the GCD is 1. And then we give those values x to x0, y to y0, r to GCD, e to a, and phi value to b, because we're going to use these in the future and put them into a general formula to find other solutions. Next, we have more functions. This function check is to check to see if x and y can be a solution for the equation. The equation says that e times x plus phi value times y has to equal 1. Because y is negative, so this is basically subtracting, and it would be able to get a 1. So this is the original equation, and the solution has to meet the original equation. If it does, then it's true and it's correct. Otherwise, it's false. So we check the solution with x0 and y0. And then it is true. So it is a possible solution. The next function is for checking the E and D, the solution we found in RSA situation. So we import random and then ed check. The parameter is D, which is x, which we will use x as D. So this function is simulating a RSA example, and the m here is a random integer between 0 and 1000, which is basically the plaintext, the ASCII code for the character in the plaintext. And we're just going to use a random integer to simulate because we don't know what the plaintext is, so we're just doing a random plaintext. So for the plaintext, one of the conditions was that m has to be less than n. So when m is less than n, we do loop equals false. So that means we have found an m that we can use, and we don't need to find more random integers. So we're going to use that m as the plaintext in our simulation. We do m to the power of e divided by n. The remainder goes to c, which is the ciphertext. And then we find the m again by using the formula. So c to the power of d divided by n has a remainder of m, and that is the m found. We're simulating the RSA process to see if the d can be used. If m equals m found, so the original random integer and the integer we found again by using the formula are the same, then we return true, and everything works. Else we return false. So this function here just checks the d to see if it would work in a real situation. The top check is to check to see if it works in the equation. So even if it works theoretically, sometimes it might not work because of a small detail. So we would need to try it in a real situation too. So those are the two functions that we're going to use to check. Here, lastly, is to find all other possibilities, other pairs of solutions for x and y. We're using x0 and y0 to express the general solution for the indeterminate equation a times x plus b times y equals GCD. So we're going to find all of or other x's and other y's that are solutions for the equation. So here's the general formula for x and y. We already know x0 and y0. So we do x0 plus b divided by GCD times t. That would give us other x's. The t is any integer. So when we use different values of t, we would get different values of x, and the values of x should all work. And then t is, it can be positive, negative, or 0. So when we use a value for t here, we would use the same value for t here and get a value for y. So that x and y pair would be another pair of solutions for the equation. And t needs to be in the integer range, so it can't be a decimal. So we're going to do t in range -5 to +5. That's 10 different numbers. We're going to find 10 pairs of x and y. So we do x0 plus integer of b divided by GCD times t. And then for y, it's y0 minus integer of a divided by GCD times t. So the a and b here, if you forgot, is a is the e and b is the phi value. So a equals 5 and b equals 24. And then we would find a lot of x and y's. For each time we find it, we use the check to see if it works. If it works, then it would print it works. So here this is the loop part. So the first time t equals -5, and the solution, after we check it, it gets true. So that means it's a possible solution. After that, we would print e, d, phi, and k. So e equals 5, d equals -115, phi equals 24, phi always equals 24, e always equals 5, and k. So we printed those four. And then if x is greater than 0, we would print the d value is greater than 0 and it is a possible value. If we check the x in ed check, that was the function for simulation for an RSA. If it is true, then we would print ed check OK. Otherwise, we would print ed check not OK. And then that would be, if it prints ed check OK, then it would mean that the x that we found, which is the d, it can be used as a private key. Otherwise, if x is less than 0 or equal to 0, then it doesn't meet the requirement and it would be an impossible value. So we could see that here, when t equals -5, d equals -115, so it's less than 0 and it's not possible. The first time when d becomes greater than 0 is when t equals 0 and d equals 5. This becomes a possible value, and after they check it inside a simulation of RSA, it also works, and so that means this d can be used for a private key. Same for these other d's when t equals 1, 2, 3, and 4. They all work as well. Realistically, we would probably choose the biggest d as the private key because we want a bigger number that is harder to crack. So now we have found d as well. Let's try some other situations. So now, for the other situation, we have more values of d, and we have also done the same thing as the first one. We checked the E, we prime factorized N, and found phi n 2. So now the P and Q are 53 and 61. Phi n equals 3120, and the E satisfies this, is coprime. And they found the solution, used the solution to find other solutions. And for this one, possible values of D are these, from 2753 to 12,113. So this also works. And it didn't take too long either. Right now it's calculating in the RSA to see if it works. And it's taking longer than before. So the last value of t is 4, so there's still 2 more to go. Right now it's at 3. The CPU is calculating a lot, so it's on the last one now. Okay, now it's finished. And the CPU got less. So this was when it was running full power, and now it's resting. So for this bigger one, it took way longer, but it still found possible values for D. And the D is also a lot bigger than before. Here it was 12,000 something, and now it's like 3 million something. So for this, it would be much more secure. For this example, the smallest one is 9,072,773. Next, let's look at asymmetric and symmetric encryption. They each have their own qualities, so how do they work together when we visit websites on computers? When we type https and 2 slashes in the browser, how do the browser client and the web server encrypt their communication? And because we use both symmetric and asymmetric encryptions, how are they used in different phases of communication? For symmetric encryption, both sides of communication share one key. The key can encrypt the plaintext or decrypt the ciphertext. Some common symmetric encryption algorithms are AES, DES, and RC4. AES is the most used. Symmetric encryption is very fast, so that's the advantage. The disadvantage is that it's not so secure. If the key is stolen, then all the data can be seen by anyone in the network, and that would be very dangerous. Asymmetric encryption is the opposite of symmetric encryption. Two sides of communication hold two different keys. The server has the private key and the client has the public key. The advantage of asymmetric encryption is the opposite of symmetric encryption. It is exceptionally secure. The disadvantage is being slower because there's a lot of calculation involved. RSA is a typical asymmetric encryption algorithm. So we've been talking about RSA for a long time. These are some of the main characteristics. 1. The private key should be kept on the server side and never be leaked. The public key can exist anywhere, it doesn't matter even if the hacker got it. 2. The ciphertext encrypted by the public key can only be decrypted by the corresponding private key. 3. The ciphertext encrypted by the private key can be decrypted by all public keys corresponding to it. So if we have a ciphertext encrypted by the private key, there are many public keys that can decrypt it. But if we encrypt it by the public key, then there's only one private key that can decrypt it. So we need to be smart when we're saying who has the private key and who has the public key. The private key is usually used to generate the signature, and the public key is used to verify the signature. And we will talk about signatures more after too. Public and private keys are relative. This means that a public key can be a private key if it is not made public, and a private key can be a public key when it is made public. So in RSA, in our code, it is like E and D, so it doesn't matter which one is the public or private key. They can be either way. Combining symmetric and asymmetric encryption. RSA solves the problem of public key distribution and ensures that the communication is secure with the correct public key received by the client through a CA certificate. Because a ciphertext encrypted with the correct public key can only be decrypted by the server's private key. So to ensure that the server is the right server, because there is only one private key out there, so if the server can decrypt our message with the right private key, then that means the server can be trusted. How to ensure that the client receives the correct public key? We need to negotiate the key for symmetric encryption by asymmetric encryption. Once the server has delivered the correct public key to the client securely, subsequent communications to ensure efficient communication then use symmetric encryption to encrypt the data. So when we're combining symmetric and asymmetric encryption, we first use asymmetric encryption to negotiate which key we're going to use, and then we can use that key to use symmetric encryption, and then it would be faster. And the process will be described in more detail later. What are digest, digital signature, and certificate? These are the three important things that are used in communication on computers. The information digest. It converts information into a string of hash values. The common digest algorithms are MD5, SHA-1, SHA-256, SHA-512, etc. Let's look at an example of it. So this is using MD5. Down here, we can put any message and it will generate a hash for us. For example, and then we can see that this message has this hash value, and it keeps on changing when I add new things or delete things. Like if I add a period, then it changes, but the length is always the same, and it doesn't ever repeat. Like whatever the message is, it has a hash that is corresponding to it. So that's like an example of hash. It has a few main things that we need to understand. First, the digest algorithm takes information of any length and maps it into a fixed length string. So even if I just have one character in it, the string for hash will be a fixed length. And the same thing, if I have a 2000 word essay, it has the same length for hash too. 2. It is possible to calculate the same digest value with two different messages. It is very rare, but it's possible for two messages that are different to have the same hash value. 3. Different from encryption algorithms, there is no decryption process. So this isn't like a ciphertext or anything. It's just converting information into a hash string. From the hash string, it is impossible to know what the original information is. So hash is used for checking completeness, because two of the same messages will always have the same hash value. So we can, by looking at the hash value, know if two messages are the same, but they're not used for confidentiality. So we can't encrypt messages using hash. We can only see if two messages are the same. Next is digital signature. So we have found the digest. If we encrypt the digest, the encrypted digest has a new name called digital signature. The signature is with the CA. We're gonna introduce the CA later too. So that's the sender. So the signature is an encryption process. The signature check is with the browser on our computer, which is the receiver, and it is a decryption process. So the sender encrypts the digest and sends it to the receiver. The receiver decrypts it and checks the signature. What is the point of digital signatures? We need to answer the following two questions to figure that out. Question 1. Why do we need a digital signature if we already have the digest? Why do we need to encrypt the digest? Answer. The digital signature and the digest are both irreversible, but the digest can be faked easily. The digest is only used to check the integrity, so to make sure the digest is correct, we must rely on digital signature. So we need to encrypt the digest so that other people can't fake it. The signature and check part are asymmetric encryptions that cannot be forged by anyone else unless they have access to the private key. So if somebody can decrypt the signature and check, then we know that they're trustworthy because they have the right private key. Question 2. Why do we encrypt the digest instead of encrypting the content directly? Because the speed of asymmetric encryption is very slow. If we need to encrypt the whole message, then it will take much longer than the time of network transmission, and it's not worthwhile. If the message is not a very sensitive information that we don't need to protect, then we can just encrypt the digest to prove who we are, and we have the private key or the public key, and we can just send the message by itself and we don't need to encrypt it. So when the content can be shown to outsiders, we can encrypt the digest at the server, decrypt it at the client, and compare the decrypted digest with the digest generated using the transmitted content. So the sender sends an encrypted digest and the message with it, and then the receiver can decrypt the digest and generate their own digest because they got the message that was sent to them, and they can compare the two digest values to see if they're the same. If they are, then the original message has not been tampered with. So they can use the digest to check if the message is the original copy. Brief introduction on digital certificates. I wonder if you found a problem in the digital signature. The digital signature is asymmetric encryption. The server has a private key, the client has a public key, and only they have signature checks. So what if the public key was given by a hacker? And when you use this fake public key to encrypt sensitive information, the hacker can intercept your information and decrypt it with their own private key. That's the problem, because you don't know if your public key is the right one. To solve the problem, you just need to make sure that the public key is trusted. You can only take the public key provided by the server, and need to know how to identify and discard the public key given by the bad guys. So that's where digital certificates come in. They're used to prove who the public key is sent from. Two other questions are needed to understand digital certificates. One, what is a digital certificate? It's basically just a .crt file. Who provides digital certificates? They are provided by Certificate Authority or CA Authority. And we can see examples of digital certificates right in our own computers. So we can go to Chrome Settings, Privacy and Security, and then Manage Certificates. So my computer is in Chinese, but it is basically the same thing. We go to Privacy and Security, go to Security, and then Manage Certificates, and then we have this pop-up. In here, we can see the certificates that our browser has. So here is the root certificates, and these are the certificates that were given to us by root CA, which is like the original CA that has like the most trustworthy certificates. So we can open any one of them, for example this one, and then it tells us the information on the certificate. So like for example, this point says it proves your identity, and then this point says it ensures the program comes from the program publisher. So like it basically proves the trustworthiness of the program. And then we can see in the details too that there's like a version. This is version 3. It has like a series code and the algorithm it used for encryption. This one was encrypted by SHA-1 RSA and SHA-1 for the hash. The one we used was MD5, and this one was encrypted using SHA-1, but it just generates the hash, so it's the same. And then it also has an expiry date. So it started from 2006 November 9th at the 17th hour, and then it expires at this date. So after 25 years it expires. So all of the certificates has an expiry date too. And here is an important part, the public key. The public key is using RSA, and here is the key. So the client keeps the public key, and the CA and the server keeps the private key, and then we can use this to communicate with them. So here we can look at all of the certificates, which is really cool. How are digital certificates applied for or issued? So when we want a digital certificate, like we are the applicant is usually the server. The server wants a certificate from the certificate authority, the CA. So first it needs to generate a private key and a public key. It keeps the private key to themselves and puts the public key with some identifying information, such as their name, their domain name, their birthday, or like, no, not their birthday, their address, and other information to prove who they are. They put that with the public key to generate a CSR file, and they send the CSR file to the CA. The CA then looks at the CSR file and checks the information in here. So they check if they're correct and if stuff like their domain name is legal. If everything is good, then they generate a signed certificate. The signed certificate contains the original information, the public key, and a encrypted hash value. So they take this document and then finds the hash value for it and encrypts that hash value with their own public key. So the CA also has their private key and their public key. They use their private key to encrypt the hash value for this CSR file. They put that with the original public key and then sends it back to the applicant. So the package of the hash, encrypted hash, and the public key is the signed certificate. And then after the applicant receives it, they have their own digital certificate. So that is basically this thing. First, the applicant generates the public key and private key pair on their own server. Then they integrate other information such as domain name, applicant name, and the public key. Never leak the private key, so they don't put the private key in it, and generate a .csr file. For example, you can generate a .csr file on here. And then they gives us a command. We just need to run this command in a terminal on our server, and it will generate two documents. The first one will be a .csr file, and the other one will be a .key, which is our private key. We keep the .key and send the .csr file to the CA authority. Right now, I have the link from the website, but I can't run it on my computer. But for the server, they would run this, and then they would get the files. They would send the .csr file to the CA authority. After CA receives the request, they will check the information. If there's no abnormality, the organization exists, the enterprise is legal, and it is indeed the owner of the domain name, then CA will use the hashing algorithm to do a hash on the plaintext information in .csr to get a message digest, which is the hash, and use the CA's own private key to encrypt this digest to generate a string of ciphertext, which is the said signature. The signature plus the .csr plaintext information is the certificate. The CA returns the certificate to the applicant, and then that finishes the application process. So next, let's talk about some details about the digital certificate. Advantages of digital certificates. Digital certificates can improve the trustworthiness of users. It indicates the recognition of certificate holders by CA authorities. So if someone has successfully gotten a digital certificate from a CA authority, that means that their information is reliable and legal, so it improves their trustworthiness. Also, the sensitive personal data from the user or the server is not transmitted to the certificate holder's network system. Only the CA and the server knows the sensitive information. So this is digital certificates are good because this personal data never gets shown to another person outside of the CA or the server. So it protects the user's identity. Where is the certificate? So we looked at it already. When we download and install a browser, the browser has a certificate from a recognized root certificate authority embedded inside the browser. If the certificate authority of a website's digital certificate is not available, then the user needs to import it themselves. So that would be a bit more complicated. They would need to make sure that the certificate authority is reliable and then import it. But it's possible to do too. And you can check out all of the certificate authorities in Chrome by going into the path we did already. Settings, privacy and security, security, manage certificates, and then you can look at all of them. Information found in certificate. Double-click on any certificate to view its contents. There's a lot of information, but the most important ones are: which organization is the certificate from? What is the public key? When does the certificate expire? Which encryption and decryption algorithm is used? So you can look at all of that information. Certificate revocation. So all the certificates have an expiry date. When the expiry date is passed, then the certificate needs to be revoked. Another way for the certificate to be revoked is when the private key is leaked. Then the certificate is no longer safe, and hackers can use it. So then the certificate would need to be revoked as well. There are two general ways of revocation: CRL and OCSP. 4. How to create CSR files. So the CSR files are the files we submit to the server submits to the CA to apply for a certificate. CSR is the abbreviation of Certificate Signing Request. That is the Certificate Signing Request file. When an applicant applies for a digital certificate, the CSP, or the cryptographic service provider, generates a private key and generates the CSR file. So that's what we did with this website here. So that was the CSP. It would help us generate the private key and the CSR file. After we submit the CSR file to the CA uses its root certificate private key to sign and generate the digital certificate. So the applicant applies for a digital certificate from a CA authority through a CSR file. After obtaining the certificate, it proves that the applicant's website is trusted and the data transmission is encrypted. Using OpenSSL to generate CSR files. So that is the website where I put in some information and then it gives us a command link. It generates a command. After local execution, two files will be generated in your local directory. The .csr is used to apply for certificates from CA authorities, and the .key is the private key that needs to be saved safely and not leaked. The TLS or SSL secures information. We often must do three things to ensure the security of information. 1. Confidentiality of information. 2. Completeness of information. And 3. Identification. The TLS and SSL combines these three components to ensure safety. Here is a scenario for symmetric encryption. So first, this is the client and this is the web server, and they want to communicate with each other. The client has a CA certificate and time and a revocation list. They also have the key, which is contained in the certificate. The web server sends them a server certificate to prove who they are. After the client knows that the server is trustworthy, they start to exchange keys. And then after they exchange keys and know which key they're going to use, they use encrypted communication with that key in using symmetric encryption. And then that continues all the way until their conversation is over. Every time they start a new conversation, they would need to negotiate a new key for the symmetric encryption. So here is the process for negotiating keys. First, the CA issues the certificate to the server, because the server needs that to prove their trustworthiness. When the client wants to contact the server, they request the identification to make sure the server is safe. So the server sends the certificate that they got from the CA to the client. The client can use that information to test if CA is trusted. So they test using the public key they have on their browser to see if the private key on the CA is correct. So they can use like the hash that was encrypted and decrypt it, and then compare that hash with the own hash they generate, and then see if they're the same. So whatever they do, they're going to see if the CA is trusted. If it is, then they send the encrypted session key to the server. The encrypted session key is the key that they're going to use for the symmetric encryption. And then the server acknowledges it. So they both know what the session key will be. And then now they can encrypt the data with the session key using symmetric encryption. And then that continues all the way until their conversation is finished. Scenario for asymmetric encryption. The asymmetric encryption part is the part that was used in the certificate. So Alice, the signer, which is the server in our example, is the CA in our example, has a private key. And then they use their private key to generate the signature, which is the encrypted hash. And then they also have the original message that they use to generate the hash. They send the message and the signature to Bob, which is the server in our example. Bob has the public key. The public key is then used to decrypt the hash, and then they have this M1, and then they compare it with the original M to see if they're the same. If they are the same, then it is true, and Bob can accept Alice. So they know that Alice has the right private key. So that's the scenario for asymmetric encryption. It is like the same logic for RSA, except the RSA is used for encrypting and decrypting the hash to compare it with the hash of the original message. Back to the original question, how do we safely visit a website? So before we visit the website gets a certificate from the CA. They request the certificate and they give the public key to the CA. The CA checks all of the information to make sure that it's correct and safe, and if it is, then they give a certificate to the website or the web server. The certificate contains the public key, the hash, company name, CA signature, and other information. And then after the web server has the certificate, the browser knows that it is safe. They would check the certificate credentials. Is the CA recognized? If it is, then they extract the public key from certificate to encrypt the data, and they can start communicating with the web server. If the CA is not recognized, then they give a user warning about untrusted credentials. So that's why sometimes when we visit websites, they would say that it's not safe. That would mean that they don't recognize the CA that the web server contacted. But that doesn't necessarily mean the website is dangerous or anything. It's just less safe. For next year, we're going to possibly discuss hash MD5. So like having an input, and then any input would generate a hash value that is a fixed length and usually different from all other hash values of different messages. And DES, which stands for Data Encryption Standard. It is one of the most popular algorithms for symmetric encryption. Thank you for staying with me for all 14 meetings, and hopefully I'll see you next year. And over here I included a picture of a woodpecker because woodpeckers would find bugs in the trees, and that's what we do in the code. So woodpeckers find bugs like us. Thank you.